Today we are given a continuous beam carrying a uniformly distributed load over the whole of its span. This beam is supported on the support A, B as well as support C. Between span AB we have a U.D.L of 6 kilonewton per meter, and between span BC we have a U.D.L of 10 kilonewtons per meter. We are supposed to plot the B.M.D as well as the S.F.D for this continuous beam, and we are going to begin with span AB. Therefore, for span A to B, for span AB, we are going to begin with calculating the maximum bending moments between span AB as well as between span BC, and we are going to begin with the span AB. And therefore, the maximum bending moment between span A and B will be given by this formula: W1 L1 squared divided by 8. In this case, span AB, that is L1, span B to C, that is L2. W1 is this 6 kilonewtons per meter. W2 is this 10 kilonewtons per meter. And this is going to give us W1 is 6 kilonewtons per meter. The span L1 is 4 meters. Therefore, 4 squared, we divide this by 8, and that's going to give us a maximum bending moment of 12 kilonewtons meter. Therefore, you get 12 kilonewton meter. Then we go to the span B to C. Therefore, for span B to C, the maximum bending moment will be given by W2 L2 squared, divide this by 8, which is going to be W2 is 10 kilonewtons per meter, L2 is 6 meters, therefore 6 squared, we divide that by 8, and that's going to give us a bending moment of 45 kilonewton meter. And after that, we are going to plot those bending moments. The bending moment, maximum bending moment between the span AB is 12 kilonewtons meter. Let's approximate it at that point, which is going to be a smooth curve. We have 12 kilonewtons meter. Then between span BC we have 45. Can go up to that point, so 45 will go all the way. It's just an approximation. Therefore, here we have a bending moment of 45 kilonewtons meter. Good. From there, we are going to determine the area of this bending moment diagram in span AB as well as that on span BC. So we go again to span AB. Therefore, for the span AB, A1 will be the area of this bending moment diagram with a maximum bending moment of 12 kilonewtons meter, which is going to be 2/3 of the base of this bending moment diagram, which is the span A to B, 4 meters, multiplied by its perpendicular height, which is 12 units. Therefore, we multiply that by 8, and that's going to give us an area of 32 square meters. Therefore, A1 is 32 square meters. Then we need bar x1, and in this case, bar x1 is the distance from the center of gravity of this bending moment diagram all the way to the end A. So that is bar x1. And in this case, bar x1 will be given by half the base of this bending moment diagram, which is half of 4. So that is going to be 4 divided by 2, which is 2 meters. From there, we go to the span BC. Therefore, for span B to C, we are going to have A2, that is the area of this bending moment diagram between the span B to C. And that's going to be given by 2/3 of the base, that is the span B to C, which is 6 meters, multiplied by the perpendicular height, which is 45 units. Therefore, times 45. And that's going to give us an area of 180 square meters. So 180 square meters. Then we determine the value of bar x2. And in this case, bar x2 will be the distance from the center of gravity of this bending moment diagram all the way to the end C. So that's bar x2, and it is also it will also be given by half the span B to C, which is 6 meters. Therefore, bar x2 is 6 divided by 2, which is 3 meters. After getting that, we now apply the 3 moment equation, the equation of 3 moment, or what we call CLAPEYRON'S equation of 3 moment. Therefore, the CLAPEYRON'S equation of 3 moment states that MA L1 plus 2MB into L1 plus L2 plus MCL2 is equal to 6A1 bar x1 over L1 plus 6A2 bar x2. We divide that by L2. And that's why we began by calculating A1 by x1, A2 by x2, so that we substitute them there. Now, in this case, this continuous beam is supported on both of its ends, meaning that the bending moment at A as well as the bending moment at C are equal, and they are equal to 0. And therefore, we are going to remain with this 2MB into L1 plus L2. L1 is 4 meters, L2 is 6 meters. MCL2, that is 0. This one is going to be equal to 6 multiplied by A1. A1 is 32 square meters. Therefore, multiplied by 32, multiplied by bar x1, which is 2 meters, and then divide that by L1, which is 4 meters. Then we add that to 6 multiplied by A2, which is 180 square meters, multiplied by bar x2, which is 3 meters, and then we divide that by L2, which is 6 meters. And that's going to be 4 plus 4, that is 10, 10 times 2, that is 20. So we are going to have 20 MB is equal to, this part is going to be equal to 96. So 6 times 32 times 2 divided by 4, that is 96, plus 6 times 180 times 3, that is going to be 540. So is equals 540. MB will be given by 96 plus 540, that is 636. So we are going to have 636. We divide by this 20 that we got here, and that is going to give us a bending moment of 31.8 kilonewton meter. So we are going to have 31.8 kilonewtons meter. So we have the value of MB, and in this case MB is going to be negative 31.8 kilonewton meter. The reason being, when this beam bends between the span A to B, the beam will sag. Between the span B to C, the beam will also sag, but at the support B, the beam is going to hog. And when a beam hogs, that is usually taken as a negative bending moment. So it is going to be negative. And then we are going to plot that bending moment at the support B, which is that 1.8, just a few units below 45. So we are going to join that point. So here, let me adjust this 12 kilonewton meter, 12 kNm. And then we join it to C. So we join it to MC again. And this is where we now have negative 31.8. So we have 31.8 kilonewton meter. So that is what we call a bending moment diagram for such a continuous beam carrying uniformly distributed load over the whole of its span. So this is a negative bending moment. This one is a positive bending moment. Whereas this one is also a positive bending moment. Good. Then from there, we are going to determine the value of the reactions. That is the reaction at A, reaction at B, as well as the reaction at C, so that we use those reactions to calculate the shear forces, which will help us to plot the shear force diagram. So we go to what? Reactions calculations. Reactions calculations. Reactions calculations. And in this case, we are going to begin with the span BC. So we say this: for span B to C, taking moments about B, taking moments about B, about support B, we are going to get what? So that's going to give us RC. Remember, you are taking moments about B from C, so that is going to be RC multiplied by the distance from C to B, which is 6 meters, plus the bending moment at the support B, which is 31.8 kilonewton meter. 31.8 kilonewtons meter. Those are those are anti-clockwise moments, and we know this, that the sum of clockwise moments is always equal to the sum of anti-clockwise moments. The sum of anti-clockwise moments is always equal to the sum of clockwise moments, and therefore these anti-clockwise moments are going to be equal to this clockwise moment. Between span B to C, we have a U.D.L of 10 kilonewton meter, and we are going to have this 10 times the span over which it is distributed, which is 6, times half of that span. So that is converting it to point load, which acts at the mid span of B and C. And is going to be RC times 6, which will be equal to 10 times 6, that is 60, 60 times 3, that is 180. We take that 1.8 the other side of the equal sign, which is going to be minus 31.8. And therefore, the reaction at C is going to be 180 minus 31.8, that is 148.2. Then we divide it by this 6, and therefore And the reaction at C is going to be 24.7 kilonewton. From there, we go to the span AB, and here we are going to say for span A to B, taking moments about B as well, taking moments about B, we are going to get what? So we get, so this is going to be RA times 4, that is a clockwise moment. So we are going to have RA times the distance from A to B, which is 4 meters, plus another clockwise moment of 31.8 kilonewton meter at B. So we add 31.8 is equal to this anti-clockwise moment of 6 kilonewton meter multiplied by the span over which it is distributed, which is 4 meters. So that is converting it to point rod. Then that point rod will act at the mid-span of the span A to B, and that mid-span is half of the span AB. Therefore, we are going to have RA times 4 being equal to 6 times 4 times 4 divided by 2, that is 48. Then we take that 1.8 the other side of the equal sign, that's going to be minus 31.8. And reaction at A is going to be equal to 48 minus that 1.8, that is 16.2, and then we divide by this 4, and 16.2 divided by 4, that is 4.05 kilonewtons. 4.05 kilonewtons. Good. Then we are remaining with reaction at B, and in this case we are going to say that the sum of all the upward acting forces must be equal to the sum of all the downward acting forces. And the upward acting forces are these three reactions. Downward acting forces are these uniformly distributed loads. So we are going to have this RA plus RB plus RC is equal to the U.D.L between A and B is 6 kilonewton meter, converted to point rod, that is multiplying it by the span over which it is distributed, plus U.D.L between B and C is 10 kilonewtons per meter, multiplied by the span over which it is distributed to convert it to point rod. And this is going to be RA, which is 4.05, plus RB, which we don't know, plus RC, which is 24.7 is equal to 6 times 4, that is 24 plus 60. 24 plus 60, that is 84. Therefore, is equals 84. So RB will be equal to 84 minus 4.05 plus 24.7, that is 28.75 is equals 28.75. And the reaction at B is going to be equal to 55.25. 55.25 kilonewtons. And that is how we determine the values of all the reactions, that is the reaction at A, reaction at B, as well as reaction at C. Now, after getting the value of the reactions at A, at B, as well as the reaction at C, finally, we are going to calculate the shear forces so that we use those shear forces to plot the shear force diagram at this point. So we are going to begin with the shear force at C. And shear force at C will be equal to this reaction at C, which is 24.7 kilonewtons. So that is 24.7 kilonewtons. Then the shear force between C and B is going to change uniformly from 24.7 kilonewtons minus the U.D.L between C and B, which when we convert to point rod is going to be 10 kilonewtons per meter times the span over which it is distributed, which is 6, and that is going to be 60. Therefore, the shear force between C and B will be 24.7 minus 60. And 24.7 minus 60 is negative 35.3. So we are going to have negative 35.3 kilonewtons being the shear force between C and B. Then from there we are going to have shear force at B, which is going to be this negative 35.3 kilonewtons plus the reaction at B, which is 55.25 kilonewtons. So we add 55.25 kilonewtons, and that is going to give us a shear force of 19.95 kilonewtons. 19.95 kilonewtons. Then we go to the shear force between B and A, which is going to change uniformly from this 19.95 shear force at B minus the U.D.L between B and A, which when we convert it to point rod is going to be 6 times 4, which is 24. Therefore, 19.95 minus 24, that is going to give us a shear force between B and A, a shear force of negative 4.05 kilonewtons. Then finally, the shear force at A is going to be negative 4.05 kilonewtons. Then, after getting the value of all the shear forces, we now use those shear forces values to plot the shear force diagram. So, we are going to begin with the shear force at C, which we have gotten it as 24.7. So, if we approximate 24.7 to be somewhere here, that is where we are going to have 24.7 shear force, 24.7 kilonewtons. Then the shear force between C and B, that is negative 35.3. Remember, the positive shear forces are plotted above this line. The negative shear forces are plotted below this line, and therefore between C and B we have a uniform change of from 24.7 to negative 35.3. So if we approximate 35.3 from this point, 35.3 units is just an approximation, so it's not that 100% accurate. So we join the 24.7 kilonewton to the 35.3 kilonewtons, and then we join it to this horizontal line, that is the line of origin. The shear force at B is 19.95, which is positive, therefore it is going to appear above this line, and it is just some few units below 24.7, so let's approximate it to be at that point, and we are going to have 19.95 kilonewtons. 19.95 kilonewtons being the shear force at B. Then the shear force between B and A will change uniformly from 19.5 to negative 4.05. So negative 4.05, where is approximately at that point, and we join the 2 points together like that, and then shear force at A also is also equal to negative 4.05, which is at this point. So we have 4.05 kilonewtons. So this is going to be negative shear force, positive shear force, negative shear force, positive shear force. Good, so that is how we plot the shear force diagram for such a continuous beam carrying uniformly distributed load over the whole of its span, whereby when we are done, we can shade off the outline so that our S.F.D becomes very clear. So thank you very much, ladies and gentlemen. We thank you for watching our video. If you are here and you are ready to subscribe, please consider doing so. And don't forget to hit the notification bell as well so that whenever we upload a new content, you will be the very first person to be notified. So let's meet in yet another lesson. Good.